So, how many of you are doing research? Okay, large amount of you, right? So you know importance of this, right? If you can get your experiment complete in minutes or hours, great, right? You can iterate quite fast. 1 to 4 days is tolerable, right? You can probably run many experiments in parallel and try to reduce the time, correct? 1 to 4 weeks, okay, only if it's high value experiment, progress stalls. More than 1 month, you don't even want to try, right? So how does TensorFlow help you here? Right, so this is what I was telling to someone here, right? Single device performance is important, but biggest performance improvements come from large scale distributed system with model and data parallelism, right? So we will try parallelism in both ways, model and data. Let's see how TensorFlow does it, right? Scalability is key to faster training, achieved through model and data parallelism. So what is the model parallelism? Okay. So we want to decrease the step time, right? Whenever we are training the model, we want to go through the training step as fast as possible, right? So how do we do it? So we try to find out what are the opportunities for parallelizing the model training, right? You want to minimize communication according to computation, right? So for example, let's say you have a model like this. If you can partition it into multiple parts and train each of the part in parallel, you can definitely achieve the model parallelism, right? I mean, you can train it faster because you are training part of the model in parallel, right? On a single core, you can use instruction parallelism. Across cores, you can use thread parallelism. Across device, for GPUs, you have PCIe bandwidth limitation, and across machine, we are limited by network bandwidth. These are some of the constraints in doing parallelism. Whenever we can't get more improvement from model parallelism, let's focus on data parallelism, right? How can we achieve data parallelism? Data is distributed across machines. So we take the model training to each of the machines where data is residing, right? Something like this. So data is replicated. So the training is run in parallel across different devices, and then we maintain a centralized parameter server where we send all the updates, and then central server updates the parameter according to updates it receives from various sources. So this we generally get for dense model 10 to 40x speed up from 50 replicas, and for sparse model we can support many more replicas. We can use as many as 1,000 replicas here. So I can show you, what happens, how you can get, faster training. So you can see that precision at 1. If I want to get, let's say, higher accuracy, right? Let's say I want to get accuracy of this 0.6. Okay. If you use 50 CPUs, you can get it within first few hours, right? If you use 10 GPUs, you get 20 hours. So it's kind of almost 5 to 6 times faster that you can reach the desired accuracy. If you use 1 GPU, you're not there even after 100 hours. Right? So you can see the effect of that, right? So to achieve this layer, you get 2.6 hours, and here you get 79.3 hours. So almost 30x speed up that you get by just putting 10 GPUs over 1 GPU. Right? You can see here 3.9x speed up at this 0.6 level, and about 4.x speed up for this particular level. Got it? So the point is that if you throw more computation at it, you can get it probably solved faster. Okay. Yeah, we talked about this. TensorFlow handles complexity for you so that you can focus on your ideas. But if you are, okay, some of you are interested in doing this, right? You also want to have control over where will you place what operation on what device, right? So TensorFlow also gives you that control if you are willing to take it. So devices are named hierarchically. So job, localhost, device CPU 0, job worker task 17 device GPU 3. So this is the naming convention of devices in TensorFlow. It's hierarchical, right? So this is typically a worker node. This is your local host. This is your parameter server. And how does it decide the placement, right? Given hints plus the cost model, right? The node execution time estimate and tensor size estimate, we take the placement decision. This is opportunity for some of you. This is active area of research, and you can come up with better algorithm for deciding more optimal placements, right? Given your cluster specification. Currently, we use simple greedy algorithm and we place it. Okay, so this is now I'm going to show you some very inspiring things. I'm sure you will get inspired to write your first model after looking at it, right? So here the task is simple, right? The image is given. Computer is supposed to come up with the description of this image, right? So look at this. So human labeler, human says that this is a close-up of 2 bananas with bottles in the background, right? Look at what best model says, bunch of bananas with a bottle of wine. So model is better, right? Model is better than humans in detecting these bottles. So it says that a bottle of wine and bunch of bananas. But when we started, it was something else. It was a close-up of a plate of food on a table. It's pretty bland, right? Look at this. Human says that it's a view of inside of a car where a cat is laying down. Best model says a cat sitting on top of a black car. Correct? A dog sitting in the passenger seat of a car. This is what the best model says. Dude. You can see this. A brown dog laying in a red wicker bed. A small dog is sitting on a chair. Right? So machine is doing better than humans in coming up with these labels, right? And these are all real examples, okay? These are not made up. These are all real examples. A man outside cooking with a sub in his hand. A man is holding a sandwich in his hand. You can see how better machines are than us, right? And initial model was very bad, a man cutting a cake with a knife. Look at this, someone is using a small grill to melt his sandwich. A person is cooking some food on a grill. Model is better, right? A pizza sitting on a top of white plate, pretty bad. Okay, a woman holding up a yellow banana to her face, a woman holding a banana up to her face, right? A close-up of a person eating a hot dog. That was the initial model. Bad. Initial model says train that is sitting on the track. Best model, a blue and yellow train traveling down the train track. Right? So true, correct? Human, a blue, yellow and red train travels across a track near a depot. You can see how much machines have come far. Right? They're matching humans or sometimes even bettering the humans. Okay, so these are some of the examples. Now the final part, we'll talk about estimator. Right? We talked about front end, we talked about canned estimator, then we talked about layers. Now we will look at this estimator framework to write your own machine learning algorithms, right? End-to-end machine learning algorithm, right? So any estimator take inputs and labels as input, then there is a model, and then there are predictions. It needs to do predictions. For model, we need a training loop, and model does also prediction, and then there has to be an evaluation loop for the model. So the estimator has a model function. There's train op, evaluation op, and prediction. So we need to define the model function for the estimator with train op, evaluation op, and predictions. Look at it. Right? So in function wise, there is a fit, evaluate, and predict function. Right? Session graphs and loops. So fit, evaluate, predict, and then we also need ability to export the saved model. We need to save the model and then export it so that it can be deployed wherever you want to deploy. Okay, so let's build an estimator for what is called as convolution neural networks. Are you aware of convolution neural network? Each one of you? Huh? Okay, so my life is easier. So what happens in convolution neural network? So there is a convolution operation, right? So I define a filter and I slide it across the image, right? And then I record the values from that filter. This is my convolve feature. Then I apply what is called as max pooling on top of that. So I find out what is the maximum value from each of the patch and use it using 2x2 filter. And then there is a fully connected layer. right? You will see, I mean, we'll implement it, right? Then this is probably a network for detecting cat or dog, a deep network. And this is my favorite slide. Why deep neural network is cool, right? You can look at this. So what you can see that each layer of a deep neural network. So look at the first layer. It is kind of learning basic compositions. It is detecting only lines, right? If you look at slightly higher layers, it is understanding compositions of the simpler shapes. So we have a complex function, and we are learning it one step at a time, one simple step at a time, right? First we are learning simple shapes, and then we are learning composition of the shapes, and then we are learning composition of those compositions. Okay, we looked at this layer 4, layer 5. Layer 5, we are able to learn much higher features of the object compared to the first 3 layers, right? First layer was just lines, second layer was maybe corners, third layer is slightly more complex composition. At fifth layer, we are able to identify fine-grained features of the images. Are you able to see it? Okay, so real model can be complex. This is deep convolution models. Okay, so we have 2 practicals. Okay, we'll do the practicals, but before that, I'll finish the other part of the course also, and then we'll come back to this practical. Okay, so I want you to know some of the tools for TensorFlow. So we talked about TensorBoard already. Then there is an embedded visualizer that you can again see in the TensorFlow. Then there is a hyperparameter tuning that is possible with TensorFlow. So for neural network, one of the problem is how do you define the hidden layer, right? How many hidden layer, how many units in each of the hidden layer. So these are all hyperparameters or configurations. So there is a hyperparameter tuning paper that Google published. It's again open. And you can take advantage of that if you are using Google Cloud. Hyperparameter tuning is automatic. And then we talked about it. We have linear logistic regression, K-means clustering, Gaussian mixture model, matrix factorization, support vector machine, random forest. These are available as third-party implementation as estimators, right? And DNN, RNN, DNN we saw, RNN, LSTM, wide and deep network. Again, they are available, okay, as part of third-party implementations. Finally, when you build machine learning model, you need to serve it, right? So once you build model, right, what happens? You have to use it in production, right? You have to use it to predict label of the new data. So what you can do is you can take the model and put it on the server. So typically you provide it as a REST API or some kind of an RPC call, okay? So TensorFlow also supports that. You can put TensorFlow on Google Cloud Machine Learning Engine or on your institute server if you have servers or on your own machines. Okay, an important property of neural network result gets better with more data, bigger model and more computations, right? Getting more data and computation is a challenge, right? So computation can be solved by cloud providers. Bigger models you can build. More data is something that is your challenge, right? But again, the way people experiment is whenever they want to build image classifier, nobody starts from the scratch. They use already trained model and use their weights, use it for learning the representation. And once the representation is learned, you use any of the standard machine learning classifier or neural network classifier to do the classification. So what happens is that imagine you have such a model that is already trained. It could be GoogleNet or ImageNet, whatever standard object detection or image recognition model is already trained. You will not train this model again, right? Instead of that, what will you do is you will set up this model using the weights and architecture that is already published. You will use that, and you will take your image, pass it through the model, and you will read the output of this network just before the output layer. right? That is not a rule that you should always do it here. You can always do it earlier also. Wherever you can cut this network and read whatever output that is coming out of that. And this output can serve as representation of an image. These are features of your image. These are like automatic feature generation, right? Or transfer learning. People also use something called as transfer learning. So you can use these weights and learn features for your image. So there is no need of human experts who look at the image and tell you what are the features. So you can use already trained model to get these features. And once you get these features, you have nothing to do with this model. These features become input to your, let's say, neural network model. And then you have to only tune the weights of your neural network. So imagine you have to write your own, let's say, classifier to detect, let's say, duster and non-duster objects. So you take some pictures of dusters and some other things and pass it to this model and figure out what are the vectors, what are the features of that. Okay, so with that, we will do last two exercises, right? We'll build one custom estimator. Again, MNIST. Okay, MNIST is a savior. Okay, let's see. You have done this already, I will not repeat this, right? I am reading the data, converting it to categorical output, right? 60,000, 10,000 test sample. Okay, this is also done. Okay, so what did we learn in custom estimator? We have to define a model function, correct? Is everyone with me? Okay, so we have to define a model function. We define in the same manner. So here we will use layers API. Right? I define first layer as a dense layer. First two layers are dense layers, right, with ReLU activation. And then I define dropout, right? And then I do logits on this, and I generate prediction, right? Now this is where it gets interesting. So we have to define mode. And mode can be predict, train. It can be predict or train. So in predict, you will use the estimator spec with the mode and ask for the prediction. So this will do the prediction for you. And then for training, you will define loss. You will define a training operator, right, which is what optimizer you are going to use. And then you are going to return another estimator spec with loss and training operator. These are set based on whatever you decided, right? And then finally you get, for accuracy, you have to give another spec, right? So when we set the specs, you know, all other logic is written internally. So you can ride on that and things become simple for you. Got it? So rest of the things are fine. So now we defined our own model, right? Now how do we really use it as an estimator? So you will see that this is simple. This is same as the other estimators, right? We use DNN classifier, DNN regressor, right? So you can see that estimator, and I'm specifying what is my model function. Okay. Anyway, go through this. This is one exercise. Take about 15 minutes to go through it, and then we'll do the last one with another 15 minutes, and I think we'll be done. Okay? Or do you want me to explain the last one also? Explain the last one also? Okay. This is super easy. This is not difficult. We again do the same thing, training. I'll just explain the part where we are building CNN. Okay, other things are kind of the same. Okay. Okay. So now what I'm going to do is I'm going to build a CNN, and I'll also use this CNN as a custom estimator, right? So this is my model function, right? In earlier case, in the previous one, we actually used layers API. Did you notice that? Yeah, so look at this. We used layers API, right? So it was still easier for us using layers API. Now we say that we will build CNN, right? Build CNN with features and mode, right? Let's look at CNNs. So here, right, I'm going to define my convolution and pooling, right? Alternatively, this is convolution, I 2D convolution, then pooling, convolution pooling, and then there is a dense layer, right? And then I apply dropout. This is what I do in build CNN. I build my CNN, and then I generate prediction, and rest of the things are the same. For predict, I give estimator spec. For train, I give the loss, same kind of cross entropy loss, and I define Adam optimizer, and finally I care about accuracy. Okay, rest of the things are the same. So I would ask you to go through these two collabs, not collabs, Jupyter notebooks. And you are a great audience. I enjoyed talking to you. I hope you learned something from the session. Thank you.